Today everyone, I am Glendon Carmen and I am to discuss PCM sample problems.
Right now, let's start with problem number 1. So problem number 1 is to determine the Nyquist sample rate for a maximum analog input frequency of A, 4 kHz and B, 10 kHz. We know from the Nyquist sampling theory that the sampling rate or the sample rate is greater than or equal to twice the maximum input analog frequency. So the solution for letter A, we have sampling rate is equal to 2f max. So we have our sampling rate is equal to 2 times 4 kilohertz, and our sampling rate for letter A is 8 kilohertz. For letter B, we'll do the same. We have the sampling rate is equal to 2 times the maximum analog input frequency, which is 10 kilohertz. Thus, we have a sampling rate equal to 20 kilohertz. Let's proceed to problem number 2. Problem number 2 is for a sample rate of 20 kilohertz, determine the maximum analog input frequency. So this is similar to problem number 1, but this time the given is the sample rate and we have to determine the maximum analog input frequency. So again, we'll say using the Nyquist sampling theory, we have Fs is equal to 2f max. We have Fs is equal to 2 kilohertz. This is equal to 2 times maximum analog input frequency. So we solve for the maximum input frequency, and that is 10 kilohertz. Problem number 3. Problem number 3 is to determine the dynamic range for a 10-bit sign magnitude PCM code. So first, the dynamic range is given by 20 log of 2 raised to n, where n is the number of bits in the sign magnitude PCM code. So we simplify this formula. We have dynamic range is equal to 20 times n log of 2. So we substitute the number of bits. So we have 20 times 10 log of 2, and our dynamic range is equal to 60.29 decibels. Let's proceed to problem number 4. Problem number 4 is to determine the minimum number of bits required in a PCM code for dynamic range of 80 decibels. And what is the coding efficiency? So first, we need to solve the number of bits using the formula that we use in problem number 3. Dynamic range is equal to 20 log of 2 raised to n. And we know the dynamic range is equal to 80 decibels. So here we solve for n, and the value of n is equal to 13.28 bits. Next is we determine the coding efficiency. So the coding efficiency is given by the formula minimum number of bits over actual number of bits. So the minimum number of bits is what we solve in the first part of this problem. And the actual number of bits is the actual number of bits that we're going to use in the PCM code. Since we have minimum number of bits as 13.28 bits, we are actually using 14 bits for the PCM code since we cannot use 13.28 in the PCM code. So we simply divide 13.28 bits by 14 bits times 100. So our coding efficiency is equal to 94.86%. For problem number 5, for a resolution of 0.04 volts, determine the voltage for the following linear 7-bit sign magnitude PCM codes. So these are the given sign magnitude PCM codes. So recall that in sign magnitude bits, the leftmost bit is what we call the sign bit. For convention, we use 1 for positive and 0 for negative. And following the sign bit is what we call the magnitude bits. So for letter A, we are given of 0, 1, 1, 0, 1, 0, 1 with a sign bit of 0, which is negative, and a magnitude bit of 1, 1, 0, 1, 0, 1, which is equal to 53. Thus, the PCM code given in letter A is equal to negative 53. Using the equation given as PCM code is equal to sample voltage over resolution, we can substitute our given there and we could solve for the unknown. So we are given the PCM code as negative 53 volts and the negative 53, and we have our resolution at 0.04. So by using the formula, we're able to solve the sample voltage as negative 2.12 volts. For letter B, we'll do the same. It has a sign bit of 0 and a magnitude bits of 0, 0, 0, 0, 1, 1, which is equal to negative 3. So again, we use the same formula. Multiply negative 3 by 0.04, and we have our sample voltage equal to negative 0.12 volts. For letter C, we again determine the value of the given PCM code. We have a sign bit of 1, which is positive, and a magnitude bit of equivalent to 1. So we have the PCM code in decimal form is positive 1. We multiply it by 0.04, which is the resolution, and we have the sample voltage, which is equal to positive 0.04 volts. Problem D will do the same. It has a sign bit of 1, which is equivalent to positive, and magnitude bit equal to 63. So the PCM code, or the decimal equivalent of the given PCM code, is positive 63. We multiply it by 0.04 resolution, and we have the sample voltage of 2.52 volts. For the last, we have a sign bit of 1 and magnitude bit of 0. So we multiply 0 to the resolution, we have 0 volts as sample voltage. And this ends my presentation. Thank you.
Hi, I'm Sean ECE122 Sol, and I'm Jeremiah Z. Ramizares, and we are here to discuss digital to digital encoding. So, digital to digital encoding. First, let us keep in mind that data or information can be stored in two ways. It is analog and digital. So whatever data we are storing or sending from the sender to the receiver, or whatever that goes through the transmission media, that may be an analog or digital signal. So, in order to transmit data digitally, it needs to be converted into digital form. So whatever we are using to communicate, technically, for say, English, in order to transmit that, we need to convert it into digital form in the forms of ones and zeros. So, the digital to digital encoding and the conversion means converting the digital data into digital signal. We now must bear in mind that the main concept of digital to digital encoding is converting digital data into digital signal. So we are just converting the data into the signals. This conversion can be done in two ways. One is line coding, and the other is block coding. So normally, for data communications, we are going for the line coding only since it is recommended by others. Next, we are going to discuss line coding. Line coding is the process of converting digital data into digital signal. That is said to be line coding. So first, we need to know what is a digital data. Digital data is found in binary format, like ones and zeros. A digital signal is nothing but a digital signal. We often describe the signals as pulses since the values in its waveform is nothing but high and low. So, here we have a simple example. As you can see, we have a sender and a receiver. Now the main task is to send an information that will come from the sender, and the receiver must receive the same information. This must be done digitally. So, in order for us to do this task, we first have to convert the information from the receiver into digital data. Digital data is what you can see there in 0101. It can be any combination of zeros and ones. Now, to convert the information from the sender into digital data, we now must use an encoder. We will now convert it to digital signal in order for the data to travel the medium, which we see in the example as a link. Now, once the digital signal reaches its destination, the signal must now be converted back into digital data. This time, we now must use this decoder for this process. Once the signal is now a digital data, we will now convert it now back into the original information, and the process is now complete. The information is now sent from the sender to the receiver. As I mentioned earlier, the line coding and digital to digital encoding are the same. Line coding are categorized into three types, which will now be discussed by my groupmate, Jemar Ramizares. Line coding has three types: unipolar, polar, and bipolar. Unipolar encoding use single voltage level to represent data. Uni means it is single. We are just using a single voltage level to represent data. The main concept of this unipolar encoding means the data has to be represented and has to be converted as a signal. What type of data and how much voltage level you require is the concept. 1. Represent the high voltage. It represents the high voltage transmitted. Whenever there is 1 in the signal, it represents the high voltage to be transmitted. 0 represents that there is no voltage transmitted in the signal. This is the gap where amplitude versus time. So in the unipolar encoding, the signal or the data that is going to be encoded transferring to signal is like this. Polar encoding. Polar encoding uses multiple voltage level to represent binary values. Polar encoding, it is available in 4 types. First is the polar non-return to 0 or NRZ. It uses different voltage level to represent binary values. It has 2 variants. A, the NRZL, and B, the NRZI. NRZL, where L means level signals in the other hand, NRZI is where the signal gets inverted. So I is for inverted. NRZL, the signal changes when the encoded binary differ from the previous bit, as shown in the graph. NRZI, the signal only changes in every input binary of 1. The difference between the unipolar and the polar encoding is that the polar encoding uses multiple voltage level, wherein unipolar uses only single voltage level. Binary values are represented in the form of signal that has to be converted and the receiver that who is going to receive. Second is the return to zero, or RZ. It has a problem with NRZ. Receiver cannot conclude when a bit ended and when the next bit is started, in case the sender and the receiver clock are not synchronized. Return to zero uses three level voltage level. The positive voltage as 1, the negative voltage as 0, and 0 voltage as none. The main difference between the non-zero to the non-return to zero and return to zero is that in return to zero, whenever the signal is started, it also ended in the full 1 bit. Third is the Manchester. This encoding scheme is a combination of RZ and NZRL. Bit time is divided into two halves. Manchester transit in the middle of the bit and change phase when a different bit is encountered. And lastly, the differential Manchester. The differential Manchester, this encoding scheme is a combination of RZ and NZRI. It also transits at the middle of the bit but only change phase only when one is encountered. Bipolar encoding. It uses three voltage levels: positive voltage, negative voltage, and zero. Zero voltage represent binary zero, and bit 1 is represented by alternating positive and negative voltages. Here we conclude the digital to digital encoding. Once again, I am Sandro C. Urbansol and I am Jamar Zira Mizares. Thank you for listening to our
Hello, I am Justin Alfred San Pedro, and today I am going to show you examples about digital encoding using some techniques that was discussed to us in the previous lesson.
These are some examples of digital to digital encoding. Example number 1. Assume that we want to transmit the following binary string 1101 001.
show the resulting signal using NRZ-L technique. In here, we can see that a binary string was given and we are asked to find out the output signal when NRZ-L technique was used. It was taught to us in the previous lesson that NRZL stands for non-return to zero level signal. We set the value of binary bit 1 to high and the value of binary bit 0 to low. In NRZL, the state changes only when the bit values changes from 0 to 1 or 1 to 0. We can see from the example that when the next binary bit is the same, like in here, the signal remains to its current state, and when it changes from 1 to 0, the signal went from high to low. This cycle continues until we reach the desired output or the conversion of the binary string given to us. Example number 2. Given the input 01, 01, 11, 01. Show the output signal if NRZ-I technique was used. This problem was almost identical to the previous one, except a new technique was introduced to us. We must know that in this technique, NRZ-I, or non-return to zero inverted, the state of the output signal only changes when the binary bit is 1. Therefore, when it is 0, the state of the signal remains the same, like in this example. We can see that from 0, the state of the signal changes when the next binary bit is 1 and remains the same when the next binary bit is 0. The cycle continues, and even though these are the same binary bit, the state of the signal changes because it was stated in the NRZ-I technique that the signal state will change when the next binary bit is 1. Example number 3. Using the RZ technique, show the signal if the binary string is 01001110. This example was also like the previous ones, which is only the conversion of binary string to an output signal. We use the RC technique or the return to zero technique in this question. This technique uses 3 voltage level, unlike the previous examples or techniques that only uses 2 voltages level. Here, we have a positive volt equals to 1 bit, a negative volt equals to 0 bit, and a 0 volts means none. The starting and the ending of the signal also happens in 1 bit in this technique. Like from this example, the signal went from 0 or low to 0 voltage before going to high with a value of 1, and the value of 1 also goes to 0 voltage before it transitioned to, to the low state with a value of 0. This cycle continues until we reach the conversion of the binary string that was given to us. Example number 4. What is the binary equivalent of the signal shown if the technique used is Manchester? Unlike the previous examples, in here, we have a output signal that must be converted to its binary equivalent. We can see that this signal is derived from the Manchester technique. This type of coding scheme uses the combination of return to zero or RZ and non-return to zero L. This means that the bit is divided into two halves like in RZ and it only transits in the middle of the bit.
and changes state when a different bit value encountered, like from the principles of non-return to 0L. We have the solution of 10100111001. This is because the first part of the signal, we can see that the state was from low to high, therefore the first bit value is 1. And it went from high to low, so therefore the next value is 0. Again, the signal went from low to high, so the next binary bit is 1. The cycle continues, like in here, we have a high state to low state, which is equivalent to 0 binary bit, and therefore, if we continue to read this signal, we will arrive in this binary string.